So hello again. Now we're going to be talking about Mealy versus Moore machines. When we create systems that are actually useful, we are going to have to deal with states. And when dealing with states, we can determine whether the state will be the output or whether we will assign a different value to the output. And that is the main difference between these two machines. So let me explain in more detail. To better understand this topic, I have the example of a sequence detector for the code 1010. What we want to design is basically a circuit that will give out an output for when the sequence is 1010 and not when it's a 0010. So let's think about kind of where are we going to start and where we're going to go. So we can agree that we are going to start in a state 0, where nothing is detected, or where basically we are starting the sequence detector. When we are in state 0, if we receive a 1, we can move on to our next state, state 1. And if we receive a 0, we will move on to the next state 2, and so on until state 4. So this is basically what we want to do. And with regards to the output, we can either say that the states are going to be the output or that we are going to assign a different output when the states change. So let me explain that further. For a Moore machine, the states will be the output. So basically the Moore machine will tell us that we are in state 0 right here, that we are in state 1, 2, and 3, and 4. However, for a Mealy machine, the states are no longer the output. So therefore we'll have a different value, let's say an added variable for the output. So let's look more closely at the Moore machine. For the Moore machine, we will have 0, whose output will be 0, and it'll move on to state 1, whose output will be 1, which will move on to state 2, whose output will be 1, 0. The output 3 will be 1, 1, so I'm basically counting in binary for each of these states. I translated to binary because we know that that is going to be a lot easier to express. And actually, in this case, we'll always need to express it in a binary value, otherwise we won't be able to have an accurate output. Finally, we have state 4, which is 1, 0, 0. Let me just write that more clearly. So now let's look more into this Moore machine. I'm going to move our initial kind of thought design so that we have more space to work on the Moore state diagram. So now we have our basic idea for the sequence. However, we are forgetting some inputs, some possible inputs. For state diagrams, we always need to take care of every single possibility. So let's look into that. First, we're in state 0, and if we get a 0, we should stay in state 0. In other words, nothing should change, because our sequence starts with a 1. If it were to start with a 0, nothing would change if there was a 1, and it would move on if there was a 0. In the next state, if we have a 1 instead of a 0, then our sequence would then be 1, 1, which is incorrect. So we would have to start our sequence over. Now when we are in state 2, we have the possibility of a 0. In state 2, if we get a 0, we would get 1, 0, 0. And again, that sequence is wrong, so we go back to our initial state. We do the same for state 3. If we were to have a 1, our sequence would be 1, 0, 1, 1, which is not correct. So again, we send it back to our initial state. Finally, we have state 4, which is going to be a little bit different from the other states. Because in this one, we don't have any case of advancing to a new state. So we can say that if the input after the sequence is completed is 0, it will stay in the state and constantly display that it is in the 4th state. However, if it changes to 1, then we consider that 1 as part of the sequence, and we advance straight into the 1st state. We see that for the Moore machine, we will need 5 states. We basically need the number of bits in the sequence and a state 0. To create a desired output where a light only switches on when it reaches a full sequence, we can say that the most significant bit is the one determining whether we get to the 4th state or not. So we just take into account this bit. So now let's try to create the same outcome with a Mealy machine, which will actually turn out to be a little bit simpler. For a Mealy machine, we see that the states are not assigned to the output. So where does the output come from? Well, we are going to assign the output, and this way we are creating a new variable that will be specifically designated to demonstrate if we have reached the sequence or not. So for our Mealy machine, we are going to say that the states are different from the output. We are going to assign the output to the change from one state to the other and not the state itself. This way, we will actually be saving ourselves from one state. So we'll have one state less. We basically do not need the 4th state. And you'll see how this works in a second. So first, let's do our kind of thought process for this circuit. We have state 0, which we can also name in binary just to visualize what we are doing. State 1, state 2, and state 3. And trust me, we will not need a 4th state. So let's think about the transitions now. Since the output is going to be different than the states, we assign the output to the changing of states due to an input. So basically, to advance in the sequence, you will have a 1 to go to from state 0 to state 2, to state 1, I mean. And we're going to say that it will have an output of 0. We're going to assign the output as the way to kind of determine if there was a sequence match for the code 1010 or not. From state 1 to 2, we need to have a 0. And again, we're going to say that the output is 0. And from 2 to 3, we are going to need a 1. And again, the output will be 0. Here is where we're able to see that we do not need a 4th state. Since the output is tied to the change from state to state, we can say that if there is a 0, because so far our sequence is 1, 0, 1, we need a 0 to get us that 1 output. So if there is a 0, we are going to go back to the 0 state because we're going to start looking for that sequence again, but also we're going to have an output of 1. And this is the difference that it has with the Moore machine. With the Moore machine, we had to add a different state to express when the sequence detector gave an actual result. But in this case, we don't need a state to express that. And then also, so this is the base of our state diagram. Now all we need to do, just like we did for the Moore machine, is determine all of the other possibilities. If it is in state 0, and it has a 0, we are going to say that it'll stay in state 0 and have an output of 0. Once we are in state 1, if it has a 1, we are going to say, actually, for this machine, that it'll stay in 1, because if you think about it, we can just consider a new sequence that already has that input of 1. This only works with the first state, because otherwise you will have kind of an actual sequence. But for this case, for the first state, you can determine that it is part of a new sequence. So that's something we did not do for the Moore machine, but we can definitely do it. I just wanted to show 2 ways of going about it and thinking about it. Then if we are in state 2 and we receive a 0, we are going to have to go back to the 0 state, because we would have 1, 0, 0. And that is not our sequence. And then finally, if we are in state 3 and we receive a 1, what we are going to do is again consider it a new circuit, but display a 0, since the sequence that we would have would be 1, 0, 1, 1, and this is not the sequence that we want. So it is going to go back to our first state, because we're considering a whole new circuit now, but it will give an output of 0. So I would just take a minute to look at this diagram and see how it makes sense for you. As you can see, there is only one case right here where there is a 1 output, which shows us that there is only one case where the sequence gives a positive output, and that is when it matches 1, 0, 1, 0. So now let's compare the two side by side and see their differences. Both of these state diagrams will have the same output. They will display a 1 when it reaches that sequence and a 0 when it does not. Remember that for the Moore machine, we're just considering the most significant bit for the number 4. However, one of them seems to be simpler than the other. As you can see, the Mealy machine will have less states. It will only have 4 states, which just symbolizes the number of bits in sequence. However, just like in this case, the Mealy machine might be a little bit simpler, in other cases the Moore machine might be much simpler. You might even consider the Moore machine simpler in this case too. Both of them have their own uses, and it is important to know how to do both ways, because sometimes you are going to need to have a different output than the states, and sometimes you won't be able to have a different output from the states. So again, very important to know. So I hope this was helpful in understanding the difference between a Mealy and a Moore machine.